Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Electricity, the spark that powers our world. Electricity is one of the most important forces in our modern world, yet it's something many people don't fully understand. It powers our homes, fuels our gadgets, and keeps our world running smoothly. But what is electricity, really? To put it simply, electricity is the movement of tiny particles called electrons, which are part of atoms, the building blocks of everything around us. Understanding how these electrons move and why they behave the way they do is the key to understanding electricity. At its core, electricity is all about charges. Atoms are made up of three smaller particles: protons, neutrons, and electrons. Protons carry a positive charge, electrons carry a negative charge, and neutrons have no charge. The interaction between these charges is what makes electricity possible. Opposite charges attract each other, while like charges repel. This simple rule is the foundation of how electricity works. Electrons, which are incredibly tiny and lightweight, can be pushed or pulled by these forces, creating a flow of electric charge. This flow of electrons is what we call an electric current. Think of it like water flowing through a pipe. Just as water flows from a higher point to a lower point, electrons flow from a place where there are more of them, negative charge, to a place where there are fewer, positive charge. This movement happens through a conductor, which is a material that allows electrons to move easily, like copper or aluminum. Conductors are essential for electricity to travel, which is why the wires in your home are made of metal. But how do we get electrons to move in the first place? This is where the concept of voltage comes in. Voltage is like the pressure that pushes electrons through a conductor. The higher the voltage, the harder the push, and the more energy the electrons carry. Batteries, for example, create a difference in charge between their positive and negative ends, producing voltage. When you connect a battery to a device, the voltage pushes electrons through the circuit, powering the device. Speaking of circuits, they are the paths that electricity takes as it flows. A simple circuit might include a battery, a wire, and a light bulb. The battery provides the voltage, the wire carries the electrons, and the light bulb uses the energy to produce light. For the circuit to work, it has to be complete, meaning the electrons need a closed path to travel back to the battery. If there's a break in the circuit, like a switch being turned off, the flow of electrons stops, and the light bulb goes out. Electricity comes in two main forms: direct current, DC, and alternating current, AC. DC is the type of electricity that flows in one direction, like the electricity from a battery. AC, on the other hand, changes direction many times per second. This is the type of electricity that comes from power plants and is used in your home. AC is more efficient for transmitting electricity over long distances, which is why it's used in power grids. While electricity is incredibly useful, it's important to remember that it's also powerful and can be dangerous if not handled properly. The human body conducts electricity, so if you come into contact with a live wire, the electric current can flow through you, causing a shock. That's why electrical safety is so important. Insulators, like rubber or plastic, are used to cover wires and devices to prevent accidents because they don't allow electricity to flow through them easily. Electricity doesn't just power our gadgets, it's everywhere in nature. Lightning, for example, is a dramatic display of electricity. It happens when charges build up in storm clouds and are released as a sudden burst of energy. Even our bodies use electricity. Tiny electrical signals travel through our nervous system, allowing our brains to communicate with the rest of our body. This natural electricity is what lets us move, think, and even feel. Understanding electricity might seem complicated at first, but at its heart, it's about the movement of electrons and the energy they carry. Whether it's lighting up a room, charging your phone, or powering an entire city, electricity is all around us, making modern life possible. By breaking it down into simple concepts, like charge, voltage, and circuits, you can start to see how this invisible force works and why it's so essential. It's a world of energy waiting to be explored. Now that we've covered the basics of electricity, how it flows, what voltage is, and how circuits work, let's dive deeper into some fascinating aspects of this powerful force. Electricity isn't just about flipping a switch and turning on a light. It's a complex and versatile phenomenon that can be harnessed in countless ways. To truly understand electricity, it's important to explore how it's generated, how it interacts with materials, and the incredible ways we use it in our daily lives. One of the first questions people ask about electricity is, where does it come from? In nature, electricity is all around us. Lightning, as mentioned before, is a natural form of electricity, created when charges build up in the atmosphere. But the electricity we use to power our homes and devices doesn't come from the sky, it's generated in power plants. These plants use various methods to produce electricity, but they all rely on the same basic principle: converting energy from one form to another. Most power plants use turbines to generate electricity. A turbine is a giant wheel that spins when energy is applied to it. This spinning motion is transferred to a generator, which produces electricity by moving a magnetic field near a coil of wire. This process, called electromagnetic induction, was discovered by Michael Faraday in the 19th century and is the foundation of modern electricity generation. The energy to spin the turbine can come from many sources, such as burning fossil fuels, coal, oil, or natural gas, harnessing wind or water, or using the heat from nuclear reactions. Renewable energy sources like solar panels work differently. Instead of using turbines, solar panels generate electricity directly from sunlight through a process called the photovoltaic effect. When sunlight hits the surface of a solar cell, it excites electrons, causing them to move and create an electric current. This direct conversion of sunlight into electricity is a clean and increasingly popular way to power homes and devices. Electricity's interaction with materials is another key area to explore. Some materials, called conductors, allow electricity to flow easily, while others, called insulators, resist the flow. Metals like copper, silver, and aluminum are excellent conductors, which is why they're used in electrical wiring. On the other hand, materials like rubber, glass, and plastic are insulators, and they're used to protect us from electric shocks. Interestingly, there are materials called semiconductors that fall between conductors and insulators. These materials, like silicon, are the foundation of modern electronics and are used to make components like transistors and diodes. One of the most remarkable properties of electricity is its ability to create magnetic fields. When an electric current flows through a wire, it generates a magnetic field around the wire. This relationship between electricity and magnetism is the basis for electromagnets, which are used in everything from electric motors to MRI machines. Electromagnets are incredibly useful because their magnetic field can be turned on or off by controlling the flow of electricity. Speaking of electric motors, they are a prime example of how we convert electrical energy into mechanical energy. Motors use electromagnets to create motion, powering everything from fans to electric cars. The opposite is also true. We can convert mechanical energy into electricity using generators, as we discussed earlier. This ability to transform energy from one form to another is what makes electricity so versatile and indispensable. Electricity doesn't just stay in wires and machines, it also powers our modern communications. Think about how your phone works. Inside it are tiny circuits and components that use electricity to process information and send signals. Whether it's sending a text, making a call, or browsing the internet, electricity is the invisible force driving these actions. The same is true for televisions, radios, and computers. These devices wouldn't exist without our understanding of how to manipulate electric currents. Beyond everyday uses, electricity is also at the forefront of scientific research and innovation. For example, researchers are exploring superconductors, materials that can conduct electricity with zero resistance. Superconductors have the potential to revolutionize technology by making power transmission incredibly efficient and enabling advanced technologies like maglev trains, which float above tracks using magnetic fields. Another exciting area of research is wireless electricity. Imagine a world where you could charge your phone without plugging it in or power a device simply by being in a room equipped with wireless electricity transmitters. This technology, based on electromagnetic waves, is still in its early stages but has the potential to change the way we think about powering devices. Electricity's ability to do work, create light, power machines, and even transmit information makes it one of the most versatile tools we have. But as useful as it is, electricity can also be dangerous. High voltages and currents can cause serious injuries or even death if not handled properly. That's why safety measures like circuit breakers, fuses, and insulated wires are so important. These devices help prevent accidents and ensure that electricity can be used safely. Understanding electricity isn't just about knowing how it works. It's also about appreciating how it impacts our lives. From powering the lights in our homes to enabling cutting-edge technologies, electricity is a cornerstone of modern civilization. The final step in understanding electricity is realizing just how deeply it shapes our world and what its future might hold. Electricity is not just a tool, it's the backbone of modern civilization. It powers everything from the smallest gadgets in our pockets to the vast networks that connect cities, countries, and continents. Its influence is so profound that imagining life without it feels almost impossible. To appreciate this force fully, let's explore its global impact, its challenges, and the possibilities it offers for the future. Electricity has transformed the way we live, work, and communicate. In the early days of its discovery, it was a marvel, lighting up streets and homes for the first time. Today, it's so integrated into our lives that we often take it for granted. Flip a switch, and the lights come on. Press a button, and your phone starts charging. But behind these simple actions lies an intricate system of power plants, transmission lines, and substations working seamlessly to deliver electricity to every corner of the world. However, not everyone has equal access to electricity. In some parts of the world, especially in rural or underdeveloped areas, electricity is still a luxury. Millions of people live without reliable power, relying on outdated or unsafe methods like kerosene lamps for light. This energy divide has significant consequences, limiting access to education, healthcare, and economic opportunities. Bridging this gap is one of the major challenges of the 21st century, as governments and organizations work to bring electricity to those who need it most. Electricity generation is another critical issue. Most of the world's electricity still comes from burning fossil fuels. which releases greenhouse gases into the atmosphere. This contributes to climate change, making it essential to find cleaner, more sustainable ways to produce electricity. Renewable energy sources like solar, wind, and hydroelectric power are growing rapidly, offering hope for a greener future. These technologies harness natural forces to generate electricity without depleting resources or harming the environment. At the same time, innovations like smart grids are revolutionizing how electricity is distributed and used. A smart grid uses advanced technology to monitor and manage the flow of electricity in real time, making the system more efficient and reliable. It can integrate renewable energy sources, balance supply and demand, and even allow consumers to sell excess electricity back to the grid. These systems represent a shift towards a more sustainable and interconnected energy network. Electricity is also driving the development of electric vehicles, EVs, which are seen as a key solution to reducing pollution and dependence on fossil fuels. EVs use batteries to store electricity and power their motors, producing zero emissions when they're running. As battery technology improves, EVs are becoming more affordable and practical, paving the way for a cleaner, quieter future on the roads. But electricity isn't just about powering machines, it's also unlocking new possibilities in science and medicine. For example, electricity is used in medical imaging technologies like X-rays and MRIs, which allow doctors to see inside the body without surgery. It's also the foundation of life-saving devices like pacemakers, which use tiny electric pulses to keep hearts beating regularly. In the lab, researchers use electricity to manipulate atoms and molecules, advancing fields like nanotechnology and quantum computing. Speaking of quantum computing, electricity is at the heart of this groundbreaking technology. Traditional computers use electric currents to process information in binary code, ones and zeros. Quantum computers, however, use the strange properties of quantum mechanics to perform calculations at incredible speeds. These machines have the potential to solve problems that are impossible for even the most powerful supercomputers today, revolutionizing fields like cryptography, materials science, and artificial intelligence. As we look to the future, the potential of electricity seems limitless. Scientists are exploring advanced materials like graphene, which could make electronics faster, smaller, and more efficient. Wireless electricity, still in its infancy, could one day eliminate the need for cables and plugs entirely. And fusion power, often called the Holy Grail of energy, promises a nearly infinite source of electricity by replicating the processes that power the sun. While these technologies are still being developed, they offer a glimpse into a future where electricity could transform our world in ways we can't yet imagine. But with great power comes great responsibility. Electricity's role in shaping society means that we must use it wisely. Conserving energy, investing in sustainable technologies, and ensuring fair access are essential if we want to build a future where electricity benefits everyone. It's not just about creating more power, it's about creating a better world. In the end, electricity is more than just a physical phenomenon. It's a force that connects us, fuels our creativity, and drives progress. From the smallest electron to the largest power grid, electricity is a testament to humanity's ingenuity and our ability to harness the natural world. It's a story of discovery, innovation, and possibility, a story that continues to unfold with each new breakthrough. Electricity is not just what powers our world, it's what empowers us to imagine, create, and achieve the extraordinary.